Now I want to talk about area of polar curves. The bottom line is we need to figure out the value for dA, a differential of area. It's different in polar than it is Cartesian. So I suppose I have a polar function, r is equal to f of theta. And I think of dA, my little differential of area, as this little piece right here. Now remember, as d theta goes to 0, this more closely approximates a piece of a circle. And in fact, in the limit, we can consider it that. So if you think about it, then a differential of theta, d theta, is to going all the way around a circle, 2 pi, as dA, this differential of area, is to the area of the whole thing, which is pi r squared, the area of a circle, pi r squared. Solving for dA then gives us dA is r squared over 2 d theta, and that is our differential of area as it relates to a differential of theta, the angle. This, in fact, is the formula that we want to use whenever we're computing the area, all right? So now let's go to an example. I call it example 2 because I've done some other stuff before. Suppose we want to find the area inside of this curve, r equal cosine theta. Well, I think we've graphed something close to r equals cosine theta before. In fact, we should know it's a petal curve, n is equal to 1, so it's got one petal, and in fact, that is a circle. Okay, if I plug in values, theta running from 0 to pi halves back to pi, I trace my circle. I have 1, 0, 0 pi halves, and then I'm back here at minus 1 pi. So I've traced the entire thing as theta has run from 0 to pi, and that's important because if you trace a curve more than once or repeat yourself in an area, then you've added up extra area. All right, so what's area? Well, area is the integral of dA, theta running from 0 to pi. Now what was dA? Our differential of area, you will recall, is r squared over 2 d theta. All right, so it's r squared over 2 d theta, but on this curve, what is r? R is cosine theta. So I plug in cosine theta for r, and I get area is the integral from 0 to pi of cosine squared theta d theta. All right, and just for fun, you recall how to do cosine squared. You have to use a double angle formula. Cosine squared is a half plus a half cosine 2 theta. I have this other half on the outside. That becomes, what, a quarter plus a quarter 2 sine cosine 2 theta. When I integrate that, I get theta over 4, add, and then this is integrated by u substitution. U is equal to 2 theta. It actually kicks out a 2 downstairs. And I get 1/8 sine 2 theta. Evaluated between 0 and pi. When I plug things in on the bottom, I just get 0 on the top. Now sine of 2 pi is 0, so I end up with pi over 4. And now we should think about this because we know what this is. It is a circle. Okay, now its diameter goes from 0 out to 1. So what's its radius? The answer is 1/2. And so the area of a circle is pi r squared. What's r? R is a half. If I put that in to my old formula I learned in high school, I also get pi over 4. Hence, I get a warm, fuzzy feeling that I've done it right. All right, let's do another example. Find the area inside of one petal of this petal curve. All right, r is equal to cosine 3 theta. Okay, so 3 is odd, therefore I expect what? 3 petals. Remember, for petal curves, if n is even, I expect 2n petals. If n is odd, I just expect n petals. So if I want to find the area inside of one of these petals, then I need to integrate with limits that trace out just one petal. Now, to trace out one petal is traced out when r starts at 0, and then it becomes biggest, and then it's back to 0 again. So I have to think about, since it's sine 3 theta, when is sine 0? Well, the answer is it's 0 at 0, and it's also 0 at pi. And by the way, at pi halves, sine is biggest. Now, so I said 0 and pi equal to my angle. My angle here is 3 theta. So if 3 theta is 0, that says theta is 0. And if 3 theta is pi, that says theta is pi over 3. So the point is, I begin my petal at 0 and I end my petal at pi over 3. All right, so what's the area? It's going to be the integral from 0 to pi over 3 of, again, dA, which is r squared over 2 d theta. But what's r in this case? Sine 3 theta, so sine squared 3 theta over 2 d theta. And again, beginning at 0 and ending at pi over 3 sweeps out our petal one time. Okay, again, we have another sine squared 3 theta. How do we integrate that? We have to use the double angle formula. It is what? 1/2 minus 1/2 cosine of what? Twice this angle, and twice that angle is 6 theta. Then I have another 1/2 that came out. I could pull that in. I end up having to integrate this. If I integrate 1/4, it's theta over 4. Again, integrating sine 6 theta, it's a u substitution. U is equal to 6 theta. du is 60 theta. It kicks out a 6 down below. And the integral of sine is minus cosine, but I've got a negative out there. That's how I get a plus cosine 6 theta over 24. And I evaluate that between 0 and pi over 3. And if I plug in the top, I get pi over 12. If I plug in pi over 3 into 6 theta, I end up with cosine of 2 pi. Cosine of 2 pi is 1. If I plug in 0, then I end up with 0 over 12, but the cosine of 0 isn't 0, it's 1, right? So I get 1 over 24. My 1 over 24s cancel, and my answer is pi over 12. And that, my friend, is the area inside of one petal, where that's the petal curve. What's the point? If you want to find the area of a petal, you have to figure out where you start your petal. That's when r is 0 somewhere. And then after that, the first time you go back to where r is 0 again. And those correspond to important points where either sine or cosine happen to be 0. Well, I think that's all I'm going to talk about right now. Next time, we're going to tackle area between